Cool. Okay. Um, Hello. I'm Sam from NYU, indeed, with some other NYU people in spirit. Um, and I'm sorry for being a floating talking head. I really wish I could be there, but I'm in Japan at an internship at the moment. Um, but yes, so I'll be talking about video game level design as a multi-agent reinforcement learning problem, or rather using multi-agent RL to do video game level design, is maybe a more relevant way of framing it for this particular audience. Um, okay, so I'm going to make some crude generalizations now to kind of motivate where this paper is coming from. Um, so how can we automatically generate content, such as levels for games? How can we do PCG? Um, I'm going to break it down into a few very broad categories. So I think about like L systems, wave function collapse, these kind of constructive methods as like good old-fashioned AI type approaches, where you've got some symbolic algorithm that's kind of, the designer has basically specified a recipe, like a constructive recipe for how stochastically some artifact, some piece of content will get generated. Um, and so that kind of requires some domain-specific knowledge on the part of the designer. Then you have procedural content generation via machine learning, which is predictive. So it learns patterns from very large human data sets. And in both of these cases, if we're interested in kind of functional constraints on the levels that we're generating, such as the solvability, for example, or the difficulty of the level, it kind of takes some implementational gymnastics to make these methods adhere to that. So it's difficult to get these global constraints kind of baked into these local constructive rules in a general way. And then in PCGML, your model's learning kind of is equally learning like all sorts of patterns in the data set, in addition to, the kind of implicit functional aspects. And even if you kind of include, uh, you know, loss terms that correspond to those functional aspects, the model may kind of not be able to pull them apart from the more general patterns in the data set. So search-based PCG is one way of being able to say, okay, I want to generate a piece of content and guarantee that it meets these global functional constraints. But search is pretty slow. If we're trying to generate something at runtime, running a whole evolutionary process is going to be pretty expensive. And so this is why we would be interested, I think, in applying reinforcement learning to PCG. So PCGRL is this line of work that uh, we've been working on for 5 years. There's other precedent for it as well in the literature, but it's one of the deep rabbit holes that I've spent my PhD going down. And this work is another kind of product coming out of that rabbit hole. So the advantage of PCGRL then, to summarize, is that the generator is fast at runtime. It doesn't require any data set. So, in theory, a designer could come up with a new kind of indie puzzle game, and they only need to specify some kind of high-level heuristics or constraints about what makes a level good or valid, in order for the generator to learn how to quickly produce levels that meet those constraints, that satisfy those heuristics at runtime. So this is how PCGRL works. Basically, we turn the task of designing a level into a game itself. So um, the agent basically moves around the board and can edit tiles on the map, and then we'll compute some functional heuristics over the level and determine whether the agent's change has kind of improved things with respect to those heuristics or made them worse. And then that corresponds to a reward for the agent. So the agent's moving around the map, taking these local observations centered around its position, editing things, and then getting feedback. And in the original PCGRL, the agent can see the entire map. So it's kind of an egocentric observation, and then we pad the map with a whole bunch of like empty tiles so that the agent can see everything. Because intuitively, if I'm building a dungeon level, I need to know like where the key, the player, and the door are in order to make sure that this level is valid or that it has a certain path length, let's say. Um, so in some follow-up work, we kind of wanted to look at scaling PCGRL up. So in the original paper, we kind of trained on a particular map size and uh, evaluated on that map size, playing with how much kind of uh, how many steps the agent could take, and then seeing how much it was able to improve levels beyond that. Um, but in this follow-up work, we were looking at kind of more out of distribution tasks. So we were interested in what kind of agents could scale well to map sizes that were much larger, smaller, or different shapes than it saw during training. And kind of counterintuitively, we found that restricting an agent's observation to a small local patch around its position actually made it more general and better able to adapt its design strategies to these different map sizes, which was kind of a surprising result. And then similarly, in a separate paper, we explored a slightly different approach. So we still framed the level design task as an RL task where there's some kind of reward coming from editing a level. But instead of using reinforcement learning, we used evolution to evolve diverse archives of these very small neural networks called neural cellular automata, which are basically just a few convolutions applied to the level. And so essentially what's happening here is that at, at each time step, every tile on the map is being edited according to a local observation of like 5 by 5 patch. Um, and so this works pretty well. You got these quite consistent patterns. It was as if the level is kind of growing over time. Um, and even though like the edits are all made based on local information, you get global coherence in the output. And so what's happening is this kind of like stigmergy or kind of agents communicating using signals in the environment that they're leaving on the board. You can see like these keys and players flying around and like, turning each other on and off, and ultimately things work out in the end. Um, so these were, this was quite a cool model, kind of a nice representation for the problem. But we were evolving them here, and each little NCA was like good at doing one thing. It was good at making a level with a certain path length, for example. And so in this work, we want to kind of bridge the gap. We saw that local observations work well for these RL agents in terms of like giving us an agent that's able to adapt to out of distribution scenarios. Um, and then we saw that NCAs are really efficient. They only take a few time steps to like edit the entire map. And so we want to kind of take these RL agents in this paper and distribute them across the map and see if we can improve the efficiency of the level design process. And so we did that, and we also found that counterintuitively, by parallelizing the task of these agents, they also became more robust. So that's basically what I'll talk about. And I guess at a more intuitive level, why would we want to make level design a multi-agent problem? I think, in some cases or in many cases, level design is can be seen as a distributed task, where you may work on one aspect of the content over here and then work on another aspect of it over here and kind of try to bring these things together in this kind of bottom-up way. And then often when humans are designing something in a slightly more abstract sense, like it involves collaboration between specialists. If you're really trying to scale a level design, if you're building a big level, you may have a whole team of people, one person like working on designing some shrub, the other one kind of like white boxing the level to figure out where the major obstacles are placed and so on. So that kind of motivates this idea of wanting to make this a multi-agent problem in part. And yeah, so we find that this self-organization kind of leads to better agent behaviors. So this is the setup. We basically use a shared neural network, or a single network here. Multiple agents on the map will take observations. We concatenate them, feed them to the network at once, and then the network outputs actions for each of these agents. We update the environment at both of these agent positions, and then we compute reward once after all of the agents have taken their actions. And so there's this shared reward between the agents. And this makes things much more efficient because in PCGRL, the bottleneck is computing rewards. So those global functional heuristics are normally much more expensive to compute than the actual process of like running the neural network and doing backprop. We're talking about like doing pathfinding computation or sometimes even doing tree search to figure out if a level is solvable. And so we use this turtle representation where the agents can move themselves around the map and make edits. Like I said, it's a shared policy. We use standard PPO. The agents are taking these egocentric observations. And they can also observe each other. We just added a channel where the agents can see where other agents are, just so they maybe are better able to kind of coordinate, avoid each other, and like focus on separate regions of the map. And so we found that, yeah, adding agents basically leads to better training performance. So scenarios with more agents, you can see they actually they're a little slower at learning, but once they catch on, they kind of surpass the cases with fewer numbers of agents. And then we evaluate them on maps that are in distribution, so these 16 by 16 maps, fixed maps of different square sizes, as well as kind of random rectangles carved out from maps of those different sizes as well. Um, and the case with three agents, performs better and generalizes better across the board in this basic setup. And you can see them that yeah, this is what that looks like basically when they're generalizing to a larger map. So one very kind of potential obvious explanation here is that scenarios with more agents basically are able to edit the map more times. So the agents are spread out across the map and they can make more edits. Yeah, you can see them in action here. In the single agent case, the agent's kind of like running around the map again and again to like cover a lot of ground, whereas in the multi-agent cases, they're moving a little bit less and they are sometimes kind of spread out and working separately on different parts of the map. So is it just this increased number of edits that's during an episode that's leading to improved performance? So what happens if we adjust the episode length to account for this and make it such that regardless of how many agents we have, we limit the number of agent edits that can happen over the course of an episode? So that's what we're doing in this table here. And we see that when we do this, performance goes down a little bit in the training distribution, where kind of multi-agent sometimes gets a little bit worse, sometimes is comparable. But interestingly, in the most extreme out of distribution cases, so all the way on the right here, when we have very large maps and random shapes, the multi-agent cases still do better. So the agents are still generalizing better. Sorry, here we go. So it's not just that the multi-agent scenarios have more time to explore the map, but maybe it's also that even if we limit the number of edits and like moves that they can make on the map, they have more different ways of being able to explore the map. So a single agent has like a certain limited number of ways that they can like fill the space of the map and traverse every cell. But when you have multiple agents starting in different positions, you can kind of combine a greater variety of space filling curves to like fill the entire map. Oops. Yeah, and so you can kind of see that here a little bit. And our hypothesis is that because they have more varied means of exploring the map, they have less incentive to kind of memorize a strict action trajectory in order to be able to edit all of it. So the single agent has basically fewer trajectories at its disposal. And given that the agents have more ways of exploring the map, this kind of incentivizes them to learn more general design strategies. Or maybe given the fact that the other agents that are not observed by these agents are taking a variety of space filling curves, this kind of forces agents to adapt to each other. So yeah, on that note, we'd expect that given that agents are not able to observe each other's actions, this kind of makes the task more stochastic and tricky. But maybe by the same token, it actually forces the agents to be more general and adaptive. So it could be that this multi-agent process is kind of injecting this useful noise into the process of level design that prevents overfitting. So it's kind of self-regularizing. There's one more potentially confounding variable that we thought about, which is reward frequency. So I mentioned that the multi-agent case is nice because we don't have to compute reward as often. And maybe that is the sparse, making the problem a little bit more sparse is helping. And so we We make it a little bit more sparse in the single agent case, but that doesn't seem to close the gap either. So something about these policies learned in the multi-agent case are truly more general. Um, and we also observe in terms of reward sparsity, we can look at the single agent case, make reward quite sparse, and it doesn't decrease performance at all in or out of distribution. So that's kind of just a nice kind of side takeaway for single agent PCGRL is like maybe we don't need to be making reward as dense as we thought we did. So yeah, that's the gist of the paper. We apply the method to the dungeon domain as well. So we were looking at the maze domain previously, where the goal was to maximize the path length over the level. In the dungeon domain, we're maximizing the solution length, so the length of the path from the player to the key to the door. And the same kind of general trends apply to the dungeon domain as well. So in terms of kind of ongoing work, we want to scale this further. Obviously, I was only showing stuff with one, two, and three agents to kind of like probe the dynamics of this multi-agent scenario. But we also have more recently been playing with like 5, 10, and 20 agents. And things look really good. They look really promising. When we have 20 agents, you see here on the right, you'll notice like how quickly the map snaps into this kind of global order through just these local actions and this local communication between the agents. But there's something tricky in these training dynamics. Like these runs aren't stable yet. And we've thought a lot about why this might be. And honestly, I think it might be a matter of hyperparameter tuning, like batch size and scale. Um, we thought maybe it's that the reward now is too sparse, and so we actually made the reward more dense, such that each agent in this 20 agent scenario was getting its own individual reward. But that actually made things a lot worse. And so I think there might be some aspect of like when the agents are kind of localized and they're getting individual reward, they become kind of greedy and selfish and start overwriting each other's actions. So that's another kind of future direction that would be really cool to explore, I think. So basically, yeah, when we're training RL level generators, distributing agents across the map leads to increased efficiency in terms of like less reward computations and the ability to more quickly edit more of the map, and improved generalization as well on these out of distribution scenarios. And our hypothesis here is that basically making the task more challenging and a little more noisy during training forces agents to learn more general strategies. But I think there's probably a lot more analysis that we can do on that note. We could take a single agent case and inject some other noise in the process and see if that actually helps the agent's learning. We could take agents from different runs and see if they collaborate with each other. Have they kind of learned strategies that are specific to the people that they've been raised up with, or can they kind of adapt to a new team of agents? We love to train like multiple different specialist agents using different neural networks, different policies, maybe different objectives that are quasi-competitive, which I think would be challenging given what we've seen when we try to make these local agents a little bit greedy. But yeah, these are interesting directions to kind of lean into the inherently multi-agent nature, I think, of level design. Yeah, thanks for listening to my talking head. Thanks so much. Any questions?
Right, thank you. We have time for a few questions. I'll try to repeat them if Sam can't hear you. Here.
Thanks for the talk, Sam. Cool work. This seems really similar to the ideas out of ensemble learning to an extent, which there's something going on different than just what we expect from ensemble learning.
Did you hear the question, or should I?
I could use I heard the gist of it, but I'd love a repeat.
Okay, Matthew was asking, this seems similar to some of the ideas out of ensemble learning. Is this producing results sort of consistent with what we'd see there? Is there something else going on with the multi-agent reinforceable learning?
Can you summarize what you mean by ensemble learning, or what those main results are? I'm not sure if I'm familiar.
We can connect separately. I think it's probably easier.
Okay, he says maybe we should discuss this later.
Cool.
Yeah. So David Tui asked, you talked about robustness at one point. What notion of robustness do you mean here?
Good question. Do I mean robustness at all is a fair question to ask. I guess yeah. I guess I I think like generalization is fair to say in some sense because we're looking at different map sizes. Um, but to say that the agents are robust, we'd probably need some more adversarial kind of like intervention. I mean, they're starting with like initial random noise. So in a sense, being able to adapt to that noise, and statistically, that's going to be like new noise during evaluation time, uh, is some level of robustness. But I think, uh, yeah, giving I don't know. We'd need to like test them on other agents or in some kind of adversarial scenario to like truly say robust. So yeah, fair point.
Great, thank you. We should move on to the third talk. So thanks again, Sam.
Thank you very much.